Okay, let's move on to this session of research talks. We've got 3 research talks in this session, ranging from inclusion to well-being. It's going to be an exciting one. So without further ado, let's get our first researcher up. I'm pleased to introduce you Professor Mike Wald, Turing Fellow and Professor in the Department of Electronics and Computer Science at the University of Southampton. Mike is going to share his latest research with us in a presentation exploring how can AI overcome barriers to inclusion. Mike, take it away.
Thanks a lot, Gemma. Good afternoon, everybody. As a Turing Fellow, I noticed that the issue of inclusion wasn't originally in one of the research challenges. So my original research was trying to look at what are the barriers to inclusion, and particularly for disability. And the reason I think disability is important is, for example, you've probably heard a lot about people talking about making algorithmic systems fair. And the UK Equality Act 2010 has 9 protected characteristics, and, for example, gender, and you hear a lot about fairness for gender. But one of the issues about disability is it's the least homogeneous. Virtually every disability is slightly different, and therefore these are often seen as edge cases or outliers. And if you design algorithms to work fairly for edge cases or outliers, they will work fairly for the average. But if you go for the average, they won't work fairly for the edge cases or outliers. I just want to compare inclusion to health in terms of various aspects. One is, in terms of disability, the medical model of disability focuses on impairment, whereas the social model focuses on the barriers created by people, society, companies, organizations. In health, there are large data sets, scans, millions of scans labeled by experts, which can train the AI. That isn't the case for inclusion barriers for disabled people. Now, there aren't large data sets, so there are big issues for inclusion for disabled people. Some of the principles, which I just want to quickly mention, is AI is really assistive or augmentative. It's helping people. And it's really vital when you're designing AI, you include disabled people, both as users, but also in actually developing the AI. And as I mentioned, again, designing for edge cases and outliers is important. Now, in the time available, I'm only going to focus on 4 areas. One is speech and sound recognition captioning, which helps hearing impaired and deaf people. Recognizing and describing images, which helps overcome barriers for visually impaired and blind people. Sign language synthesis and recognition, which helps deaf people whose sign language is their main language. And autonomous mobility guides for blind people. Now, there are loads of other barriers and loads of other areas, but in the time available, I'm just going to focus on these 4. Now, you've probably all seen speech recognition being used for captioning on Zoom or other areas, and it's got very good. There's a paper here by Microsoft a few years ago, which said it could be more accurate than human transcribers. Now, that works for very high quality speech, low background noise, but when you get difficult conditions, then humans are a lot better than AI at the moment. And this is an example of some research done by Microsoft, which is using virtual reality to project the captions above the speaker. So one of the problems a deaf person has at a meeting, for example, by the time they can work out who's speaking, they've already spoken. So just having the captions of the list doesn't really tell them who speaks. You can have the name of the speaker, but this is another way of doing it. AI can identify speakers. It's called diarization. And here the red and the yellow are showing 2 speakers. And it's pretty accurate, 92% accurate in this case. Deaf people also need the sounds to be captioned. And YouTube, for example, can captioned laughter on some of its automatic captioning. Deaf people and hearing impaired people also miss out on the emotion. When you're listening, you get the emotion. When you just see the text, you don't. And this is an example where the colors show different emotions, and the original website allowed you to hover and click on things and you could hear the speech. And the problem is, how do you show the complexity of emotion in a caption? Do you use colors? Is it too much information? And face emotion detection is useful for somebody who's visually impaired or blind, but is telling someone that this face is 7.77% happy, angry, neutral, and different percentages. How do you present that information? Now, lip reading is very important for deaf people, but AI can do it quite well. And in this example, LipNet had 93% accuracy, whereas an experienced lip reader only had 52%. And this is a test of artificially produced. You've got a face and a clear background, just speaking sentences. In a more realistic situation, this was some work DeepMind did. This is a video of BBC News. And if you count the errors, it's 22%, but they're very minor errors, it's and in. So you get 100% of the meaning. And so the AI is doing very well here. And on the left, it shows with no background noise. On the right, it's with background noise. And this is word error rate, so the lower the better. And in noisy audio, adding the lip reading improves the accuracy by 10% and reduces the word error rate. And you probably know this. If you're in a noisy place, you look at people's lips because you're missing things through your hearing. Now, that's with ordinary cameras and just a flat video, but 3D cameras are available on phones now, and that would improve the lip reading of AI using 3D cameras. Now, I imagine most of you have seen these deep fakes where you actually find that somebody has altered the speech, the facial movements, and the speech of somebody. And there are examples on the web. But you could actually use this to improve someone's lip readability. If they mumble and they're very difficult to lip read, you can make them easier to lip read. And these systems work on having an input source and a target and mapping the faces. Now, image recognition, again, helping blind people. In this case, you can see on the left, there's an image and there's 4 boxes drawn around objects. And it's saying it's at 89% sure there's one person, it's 73% sure about another person, 67% sure there's an umbrella there, and 56% sure it's a table. It hasn't identified it as a table tennis table, but it's a table. Now, again, giving that information for a blind person might be useful, but if you have a video, for example, the frames are changing very fast. So if you're trying to describe a video for a blind person, you can't give that much information. In this case, it's managed to identify the keywords outdoor, beach, water, ocean, wave, shore, sandy. But it's more useful for people to actually put it together in a sentence. And on the left, you see a training set and some examples there. The top one says a cute little dog sitting in a heart drawn on a sandy beach. The middle one has a dog walking next to a little dog on top of a beach. And the bottom one, a large brown dog next to a small dog looking out a window. And the automatic captioning of the test image on the right says a dog is sitting on the beach next to a dog. So this is a bit more useful than just having keywords. And you can see the colors are trying to show where the different informations come from. Now, movie audio description is very challenging. If you're blind and you're listening and watching a movie, there is some information shown visually that you're missing, and very skilled human audio describers will describe it in the gaps between the speech. The problem trying to do this automatically is deciding when the visual information is vital, because there's too much visual information to explain. And as an example, if a person leaves a room, it's important to know whether it matters for the plot. So, for example, if something is said while they're out the room, then it's important for the viewer to know that. So an automatic AI audio describer would have to understand the meaning and the plot, and it's a lot more complex than just describing images. Sign language translation is very difficult. You've probably all tried Google Translate and other translation systems, and they have masses of training data because they have parallel text from written languages. They don't exist because sign language is a visual language. So this is a hard challenge for AI. And mobility guides for visually impaired people. So a visually impaired person, a blind person, uses a cane or a guide dog or has an assistant, but we have autonomous vehicles which can navigate. So it would be very useful to use this sort of technology, for example, on a suitcase, to help somebody navigate an airport. And as a final thought, it's really important to have diverse, inclusive people designing the artificial intelligence and machine learning. And the British Computer Society, that's a quote, they were talking about MSc conversion courses, but it's generally important. So I'll stop there and have time for any questions.
Thank you very much, Mike. That was really fascinating and chock full of examples, which has been brilliant. We've got our first question through on the slide. We've got time for questions, a couple more questions though. So if you want to send one in, please do start typing now. I know there's a little bit of a delay and get that sent over. That would be great. So the first question that we've got here on the Slido is from Anonymous. It says, does the AI perform the same across different languages at captioning, or are some languages found to be more challenging?
Yeah, I mean, there is a huge problem with minority languages. The problem is for captioning speech, you need large quantities of labeled speech. Now, deep learning has made this a bit easier, but basically, again, you need examples. Now, in the past, people were using subtitles from television as training data. But anyone who's used subtitles knows they're not actually word for word. The other thing is speaker independent captioning is what most people are using now. And of course, people have different accents. For example, English has lots of dialects, and if you're having lots of different people speaking it, for the system to get it accurate is an issue. So one of the issues with automatic speech recognition is how you edit and correct the mistakes. Because, you know, saying, oh, it's 90% accurate, but that means 1 in 10 words are wrong. And for example, if it's getting the negative not wrong, it's missing it out, you've totally given the wrong information. So there are, you know, it looks good, but you need to think about how you can correct it. And there is a huge problem with minority languages.
Yeah, I can imagine it's a big hole to fill. I mean, even I'm actually partially deaf in one ear, and I use subtitles every time I watch the telly. They're always wrong, always wrong. You know,
no, it's worth saying that the BBC have done tests, and I think about 30, 40, 50% of people use subtitles and captioning. The difference between foreign language subtitles and captioning is assuming the person can't hear the sounds as well. Whereas with foreign language subtitles, you can hear the sounds,
yes,
you can hear the emotion, but you're just giving the words. Now, I use it all the time because quite often people put background music, and I hate it. They do it on YouTube videos as well. People try and get all creative and put the background music, which, and on movies, often the background music is so loud, and actors are whispering, it's quite difficult. So I tend to have it on. They've also done research that showed it's a good way for people, and particularly children, to learn languages through the subtitles.
Yes, yeah, exactly. And it's interesting what you said about the hearing the emotion if it's a foreign language versus, it's interesting when you're watching something in English, knowing English, hearing English to some degree and seeing it. And actually sometimes it can be very distracting when the subtitles are almost paraphrased or aren't correct. It's normally when they're paraphrased, there's a delay or something.
Well, the reason they paraphrase them is they're trying to, the human subtitlers paraphrase them. They don't do it word for word because they're on a television, you only have 2 lines, and they want it to appear for long enough to read it. They also don't want to distract from what's going on the screen as well.
Fair, a difficult balance, I'm sure. Let's got a couple of questions here. Let's turn to the Slido. We've got another one saying lots of really interesting topics here. How do we know where to start? Do we choose the largest group or the most disadvantaged historically? It's a good question.
When you say we, are you talking about researchers?
I guess so. I mean, society.
Well, again, it depends. If you're a commercial, I've been working on using speech recognition for lectures for students and finding ways to caption them for years, and nobody was interested. And so in the end, a lot of commercial companies end up looking where the market is, who's got the money. And that goes again to this issue about minority cultures and languages, if they haven't got the money to pay for it. For example, it's much easier to have an autonomous suitcase than it is to have an autonomous vehicle. But is Tesla going to develop an autonomous suitcase for blind people? Elon Musk could do it.
Yeah, good point. Good point. Nice, interesting point to end us on, though, I'm afraid, Mike, because we have run out of time for your presentation. But thank you so much for presenting such interesting topics. Anyone who asked a question on the Slido who I didn't get to, we might have some time at the end. And if not, I'm sure Mike could be happy for you to email him or ask questions directly if it's something about his work. So moving on to our next presentation, we're going to welcome Jonathon Lawry, who is Professor of Artificial Intelligence from the University of Bristol. And his research talk is called It's Good to Talk on the Principles of Collective Learning in Distributed Autonomous Systems.
Okay, thank you very much, Gemma. So I guess what I'm going to talk about today is a collective perspective on AI and learning. So here's a couple of pictures. Here's Rodin's Thinker, which is a sort of very popular image of the kind of individual thinking their way or learning their way to the truth. And here's Raphael's School of Athens, which is about dialogue and the Socratic method and people learning together and arguing together and finding finding about the world in that way. So what I want to do today is talk a little bit about collective learning in AI and robotics. And I want to try to sort of tentatively suggest some very simple principles that it might be good to satisfy in collective learning. And these are not at all meant to be the sort of last word on this issue at all. Really, they're just sort of put out there for debate and to just try to help us sort of focus on some of the issues. So here's an example of collective learning, or what might be a collective learning problem in robotics. So imagine we've got some number of drones here, that they're searching some environment for casualties. So maybe this is a search and rescue problem. And so the drones, they go off and explore the environment. So they've got sensors and they find out about the world partly in that way. But they interact with each other, they communicate and share information. And so we have these kind of two processes that are going on. And that gives us a way of sort of thinking about how the whole system learns. So just to sort of re-emphasize that, then we're going to think about collective learning, particularly from these two perspectives. We've got learning from the environment, which is sort of updating, so robots going out and taking sensor measurements or whatever, and also agents interacting with each other, sharing information, and sometimes fusing their opinions or beliefs about the world. So these kind of two processes. Okay, so I want to also sort of just very briefly introduce a couple of types of a collective learning problem that we're going to think about. So the first is called the best of N problem, and this is actually partly inspired by biological systems like honeybees, which what they do is they collectively go out and decide which is the best new nest site out of a number of possible options. They do this collectively. Bees fly off, they get information about the different sites, they come back and they share this. And part of the mechanism by which they share this is this famous waggle dance, where they perform a strange dance which communicates all sorts of information, like the quality of the site they've visited is partly communicated by the length of the dance, and the direction is also partly communicated. So I want to show you an example of some robots actually performing a video of some robots actually performing the best of N problem. So there are a number of options here, different locations, 1 to 5, and what they go off is they go off and visit these locations. They visit them in pairs, and you can imagine them getting some numerical value at those locations about the quality. And based on that information, they then come back to the center and they combine their information, they share it and combine it together. And you can see, and gradually over time, you get a consensus, and the whole system converges on a solution. So that's one type of problem I'm going to look at very briefly. And another is called the state of the world problem. And here's a little square at the bottom, kind of representing possibly a grid, a map grid, and in different locations there may or may not be casualties. And what the robots will be trying to do then is go around and somehow build up a shared picture of the world, where all the casualties are and where they're not. Okay, so I promised principles, so let's have a go at one principle, and that's that the evidence is king principle. And the idea of this principle is that information from other agents should help to facilitate and not inhibit the spread of direct evidence from the environment. So there are various ways. So the idea here is that evidence is spread by the communication, and it should be helped to be spread. So there are various versions of this, one of which is an idea called evidence preservation. And if you've got two agents with some beliefs about the world, and if one of them gets some information and then they combine, they fuse, that should be the same as essentially if they combine their beliefs first and then afterwards they receive that piece of information. So that's one way of thinking about evidence being preserved and propagated. So here's a simple kind of illustration of that kind of process happening. Here we've got agents which are trying to learn whether or not a particular proposition is true or false. And so the blue line here is, so what we're here is that their agents are estimating the probability the proposition is true. It turns out to actually be true. So 1 is good and 0 is bad here. So the black line is where the agents are combining these two processes of fusion and evidence, and the blue line is where they just have evidence on its own. And you can see that this is what you'd sort of want to happen. You get improved learning, speed of learning through combining these two processes. So that the fusion is helping to spread the evidence in that sense. So here's another principle, and this is called the disagreement leads to doubt principle, which you might want to consider. And this says, well, that if an agent receives information from other agents that's inconsistent with its beliefs, then it should become more uncertain. On the other hand, if it gets consistent information, it should become more certain. And there's a sort of caveat with this, that really when it's uncertain, or it's uncertain about particular aspects of the world, it should try to go off and find out new information about those aspects of the world. So here's a very simple version of this problem. So supposing we've got three possible outcomes, let's call them S1, S2, and S3, and agents' beliefs in this model, they are represented by sets of these options. So this agent here believes that the best state of the world is either S1 or S2, but not S3, and so on. So for example, if this agent met another agent who believes that the true state of the world is, or the best state of the world is actually S2, then what you do is you get an inconsistency, so you become less precise. You think that you go to take the union of these. And if you meet an agent that you agree with, so S3, so that's consistent, then you become more precise. And then you can combine that with an updating method where you say, suppose we have an uncertain agent here, then what's going on here is that this agent is saying, well, actually what I'm going to try to do is I'm going to visit two sites, two of these options like the robots, and I'm going to measure them, and I'm going to eliminate the one that was the worst, because I now know that that is not the best site. So that's an example of a model, and you can put these kind of things together into mathematical models. And if you do that, you can sort of study the whole system. So this is a sort of plot of the proportion of agents in the system that are completely uncertain here and that hold other beliefs here. So in this case, the right answer is that the best state is S3. And you see that total uncertainty declines. You get some intermediate levels of uncertainty here, and then you get growing certainty in the correct answer. Okay, so one more principle is the idea of the robustness principle. So the idea that these systems should be robust to noise in the environment and malfunctioning and even to malicious agents. So here's some experiments which we ran using very small little robots called kilobots, a big swarm of 400 of them. And what we did there is we tested the robustness to malfunction. And what we showed was that if you allow agents to at least represent their uncertainty about the state of the world, so in this case there was a simple binary choice, one location or the other, if you like. And so if we allowed the agents to have a don't know option, then that made the whole thing much more robust to evidential noise. So that's another, I should say robust to malfunction. But you also might want to be robust to evidential noise, and this is an example of that. So this is the state of the world problem, where you're trying to get the agents are exploring this environment, these cells, trying to discover whether casualties are there or not. And through this process and through this distributed learning process, there's a certain noise level, so that when you visit each of these cells, there's a 20% chance you'll get told the wrong answer, i.e. that there's a casualty there when there isn't, or vice versa. So this is sort of error, if you like, here, and this is the number of agents. And basically what you see is over time, that as you increase the number of agents, there's the collective learning essentially corrects for errors to some extent. Another principle potentially is the idea that we should be robust to changes in the environment. So what we need to do is to ensure that with collective learning, that there isn't so much reinforcement that agents end up being completely certain about the world, so that if the world does actually change, they can still adapt to this. So, for example, we've experimented here with using, rather than agents having pure probability distributions, having probability clouds, if you like, second order probabilities. And this allows them to better adapt to the situation where the environment changes. Okay, so finally, I wanted to give one more principle, I suppose, one more specific one, which is the connectivity principle. And this says that it's good to be connected, but rather counterintuitively only in moderation. So we've been doing some experiments in this context with small world networks, looking at networks of connectivity in agents and saying, well, is it always best for agents to be fully connected so they can always share information with everybody, or is some other model better? And what we've been looking at here is graphs of connectivity, which are where you can have different numbers of neighbors to which you're connected. And again, this is an error model, and you can kind of see these sort of shapes here where too low connectivity, you don't get enough of these kind of error correction effects that I've already mentioned. But too high a connectivity, you're also getting sort of suboptimal performance. So somewhere in the middle, there's an optimal amount of connectivity, an optimal amount of interaction between agents. Okay, so I suppose I want to summarize in a sense with one sort of overarching principle, and I think it's a debatable principle, and that's a sort of meta principle that of all the principles we've talked about, they're kind of judged on the extent to which they enable both individual agents to learn, but also the whole population to learn. So we've got both of those things going on. So you could say, well, maybe that's not always what you want. Perhaps, there can be situations where it's better that you would have some agents in the population that are just wrong, and maybe that can help the population as a whole adapt to change, for example. Maybe some aspects of competitive learning are also useful. We certainly know that in AI in other contexts. So I think, what I hope I've shown is that by exploring some of these collective learning principles, I've kind of highlighted some of the issues around collective learning. And I wouldn't want to claim at all that these are, well, even correct, but certainly not exhaustive. And some of the times they may not be consistent with each other, but I think they're a useful tool for at least thinking about different aspects of collective learning in AI.
Jonathan, take it away. Thank you very much, Jonathan. That was really, really great. Let's move over to some questions now we've got come through on this Slido. So the first one is from Reese. How does the updating actually work? Is there an application of Bayes' theorem somewhere in there? Yes
and no. So we've explored lots of different models, including probabilistic models. So I think one of the first graphs I showed you was a probabilistic model. And in that case, the evidence updating is entirely Bayesian. And then the probability, the fusion operator is also a way of pooling or combining probabilities. So in that specific context, you can then try to address these kind of principles or think about these principles. So, this evidence preservation principle is actually quite interesting to think about in a probabilistic setting. And it turns out that there are some really nice results. So in fact, it turns out that providing you make a symmetry restriction as well, in other words, that when you when you fuse these two probabilities, it doesn't matter which way round you do it. If you make that requirement as well, then what happens is that you're very restricted. There's only really sort of one pooling operator that gives you this way of preserving evidence, for example.
Awesome, thank you. We've got a few questions coming in now. That's great. This one is from Rory. Has the idea of having agents with different weightings been explored, such as having?
Yes, and it's quite interesting. So, I mean, so there are definitely contexts where that works, and it's interesting to think about. It's again easy to incorporate into probabilistic models, but you can do it more generally. In some contexts, it helps learning, but in others, it doesn't always, because so one of the things that's quite interesting is this, if we go back to this disagreement leads to doubt principle. So what the reason that can be helpful is that if there's noise in the environment, you tend to get inconsistency. So you want to actually encourage agents to meet and recognize that inconsistency. So sometimes if you weight agents, that can slightly dilute that effect. So it's not as simple as saying it's always the case that weighting, agents actually improves performance. It depends somewhat on the context. But it's certainly something that you might want to do if you've got specific prior knowledge about how effective different agents are.
Expert agents. Amazing. Thank you very much. Let's go on to our next question, which is from Julio. Very interesting talk. Thank you. Could you comment on the difference between distributed and collective learning and federated learning?
So I don't know. I'm not sure I'd want to massively distinguish all of these terms. So I think this is distributed learning. I guess that perhaps in collective learning, there's a bit more of an emphasis on looking at the system level, so there's a lot of tools there's a lot of tools that we use that are perhaps taken from complexity science and things like that. So maybe there's a different emphasis there, but I think a lot of these terms are really addressing very similar ideas. Maybe they're just coming from slightly different academic literatures and perspectives, but I think that I wouldn't want to sort of, I wouldn't really want to sort of emphasize the difference between them. So I think there's a real, but sort of definitely between distributed learning and collective learning, I think there's a real kind of, there are definitely big overlaps.
Awesome. Next question from Jason. Is this collective learning method strategy proof? Can agents benefit from deceiving others in some instances of these problems?
Gosh, undoubtedly. I mean, so a lot of what we've looked at has been collaborative, but of course, you can easily think of scenarios where that may not be the case. Even sort of not particularly. You could imagine scenarios, for example, where we've got, driverless vehicles that are owned by different companies, and they're all trying to find the optimal route. So, some kind of element of competitive behavior is definitely interesting there. And we've certainly got, so I've got some students, for example, that are looking at how agents, might compete in exactly that kind of road allocation problem. So you then, there are probably other principles that at play here. And a lot of those that I've talked about today have really been focused on this kind of shared collective endeavor approach. But, there are definitely, other interesting scenarios where it's much more competitive.
Thank you very much, Jonathan. That's all we have time for you today. But thank you so much for sharing your presentation and answering questions. Again, there's a few more on the slide that we didn't get time to get to. I'm sorry about that, but I'm sure Jonathan would be happy for you to reach out if you have any questions directly. So let's go to our final, our last but not least speaker is Dr. Chanuki Illushka Seresinhe. She's a visiting researcher at the Alan Turing Institute and the Director of Data Science at Culture Trip. She's bringing to us a presentation titled AI to Understand Beautiful Places and Our Wellbeing. Chanuki, take it away.
Great. Well, thank you so much for the introduction. So I'll just get going. So yeah, so for centuries, I just realized. Oh yeah, so for centuries, humans have expressed their appreciation for beauty in their art, literature, and philosophy. Governments around the world, they value beautiful places as evidenced by protection of beautiful places. And also architects and designers often emphasize not only the utilitarian function of buildings, but also the aesthetics of the buildings they create as well. So it's pretty clear that beautiful places are really important to us because, you know, we do seek them out ourselves, just even when we want to just lift our well-being. But until now, we haven't actually been able to provide any quantitative evidence on a large scale supporting the idea that beautiful places might actually be beneficial to humans, as we previously have been lacking data on the beauty of our environment. So normally when we look at data on the environment, we tend to focus on things that are a bit more easy to measure. For example, green space, distance of parks, land cover types, or measures of biodiversity, because they're objective and you can kind of quantify them on a very large scale. But you can imagine that if you wanted to gather data on the beauty of an entire country, that's a lot more difficult because you normally would have to ask people, you know, is your neighborhood beautiful or not beautiful? But luckily these days we spend a lot of time on the internet. So now the internet has become a really fantastic source of actually allowing us to gather data. So I was really excited to come across this website called Scenic or Not. And it's this website that basically people can rate images between 1 and 10. But what's happening in the background is that we have an image for every square kilometer of Great Britain. So by the time I came across this data, there are about 217,000 images with about 1.5 million votes. So it's quite a nice, quite solid data set of beautiful places around the world. And so if we map this data out, you will see kind of patterns emerging. And it tends to be the places, you know, people might like to go on holidays or people might like to go hiking. So, you know, you've got the Lake District and the Peak District. You also have areas like Somerset and Devon, for example, as coming out as being quite beautiful. So even that one image is giving us quite a good sense of data. But, you know, I'm really interested in understanding what beauty might mean for people that might live in cities, because most of us, and then the end of the day, do live in cities. And if we think about one image per square kilometer in a city, that's really not going to be representative of beauty in an area. So I was wondering if I could actually generate beautiful ratings. So I wanted to use convolutional neural networks to help me predict the beauty of new images that we don't have any ratings for. So normally when you train convolutional neural networks, you know, you tend to need millions and millions of examples, and I only have about 217,000 images. So I use a technique called transfer learning. And with transfer learning, all you do really is that you can train a neural network that can already do something quite similar to learn how to do a slightly different task. So with this neural network, the base neural network is actually something called Places. So it's from MIT, and it can already do a very good job of actually recognizing different types of place categories, for example, tower or bridge. So I basically then retrained this network instead to predict beautiful scores, and it did a pretty good job. So it was actually able to predict where the beautiful places are around England at a higher scale. So let's look at what the results look like. So I wanted to kind of just give the neural network all the images I could find of London. So I sourced these images from GeoGraph, and I kind of mapped them out. And I wanted to see, you know, are the predictions going to be intuitive for what we might find beautiful around the city? So one of the areas right now, especially in lockdown, I like to go to walk to is Hampstead Heath, and because I find it very beautiful, I find it uplifting to visit. And if we look at how the neural network does to predict beauty in the area, you'll see all around Hampstead that's predicting beautiful places. So purple is like super scenic, green is very scenic, and gray is not scenic. So all around we've got the roads and that's networks, and that's not coming out as scenic. But you do see beautiful areas, for example, this lake, the Hampstead Heath ponds, as coming out as being a beautiful image that the neural network can pick up. So let's look at how this looks like across central London. You'll see, obviously, of course, parks are going to come up, but there are some trails that I saw, and there were these paths where there's tons of green dots, and I was wondering, like, what is that? Like, was that like a really beautiful road? And well, it turns out it's Regent's Canal. So it's not only picking up on beautiful parks, of course, that are nice to spend time in, but other types of beautiful structures as well that we might find beautiful around the city. And then finally, it knows to tell the difference between, it's not just picking up on the beautiful park just because there's green, there's grass in the area. It can tell, like if it's a green area, but if it's next to a network, or if it's looking a little bit dilapidated, it's able to kind of differentiate the difference. And then finally, I also looked at kind of was honed in on some more built up areas. So for example, Tower Hill is a very beautiful area as well. And, it's also picking up that characterful building should also be beautiful. So it's done a really good job of kind of, helping to predict beauty around a city in quite a flexible way. So if we look at the predictions I have for the images in GeoGraph, you'll see, okay, it is doing, a good job, but the GeoGraph images are still kind of sparse in certain areas and a bit spread out. Again, not really great for research purposes because some areas are not represented here. So I wanted to try and use Google Street View images instead. So when I immediately trained the neural network, before training, I just gave the neural network images from Google to predict, and it just couldn't get it right. It was, the accuracy dropped to 0.26, and it was just really getting confused. And just generally, when you're training neural networks, they're very sensitive to the type of image. So a GeoGraph image is a certain type, and Google Street View images are actually kind of images stitched together. There's a lot of distortion in the image. So that was actually kind of making the convolutional neural network confused. It looked like a completely different image for the network. But very simply, we just had to gather more data. So here we just kind of, all we need to do is gather another few thousand images with Google Street View Network, and we got them rated. And it improved the accuracy. And then I was able to kind of build like a very good map. Like if this is London, and I know where the beautiful areas are, and I know where the beautiful areas are not. So it kind of helped to give a nice representative ratings. So yes, it turns out that beauty isn't in the eye of the human beholder only. You can actually train AI to recognize beauty, which was kind of surprising, but not too surprising because there are some patterns as to what we prefer. So one of the kind of papers I kind of wanted to use this kind of beautiful ratings was to look at beautiful environments have a quantifiable association with increased happiness. And I had this like really great data source to work with. And this is data from an app called Mappiness that was built by Jordan McCarran and Susan Murata when they were at the LSE. And here people are just pinged 2 times a day and they report how happy, relaxed, or awake they are. I was focusing on happiness. And they also answer a few kind of questions like, are you alone? Are you, with your spouse or your children? And basically, what are you doing at the time? Are you working? Are you, doing errands, traveling? So it's quite a rich data set to kind of work with. So if you look at kind of happiness over time, you'll see basically, people are not so happy in January and February, and they start to become a lot more happy in the summer. And if you look at happiness over the week, obviously people are much more happier on the weekends, less happy on Monday, Tuesday, and Wednesday, I guess, when you're working. Just kind of, I guess, how it goes. So it was just a really fun data set to work with. So the way I did the analysis, I used was a fixed effects analysis, and I'm measuring, because I'm able to measure happiness in real time for each individual. And I can control for a range of variables, such as, whether they're at home or at work, or activities they're doing, because the website, the mobile app is actually quite rich with the data it collects. But luckily, because it is a mobile phone app, you also have the GPS signal giving you the latitude and longitude as well. So we can use this to link with other types of data that we also want to control for. So for example, I want to know if somebody's happy because they're in a beautiful area, not just because they're happy because they're it's a sunny day and they're basically out with their their spouse, for example. So we want to kind of hone in as much as possible to look at the effects of the beautiful place itself. And it worked out. So it turns out that we were able to show that individuals are significantly happier when they visit environments that are more scenic. And this did actually held as well for built up areas as well, because that's what I was very interested in, is that I didn't want it to be that you only can go to the countryside and of course there you're going to be happy. I wanted to see that this actually held in the cities, and it does. So what are the implications for policy with this research? So can we use AI to understand what is actually beautiful? So again, I went back to my data because I have about 217,000 images. So I want to understand, what are we finding beautiful? Are we able to use that to provide anything that's kind of meaningful as a guidance? Again, I went back to that neural network before that I mentioned from MIT called Places, which does a really good job of predicting different types of places. And I also can extract another level of features here as well. For example, is it a man-made or natural? Is it an open area? As well as many different things about the kind of the material as well. So it's quite a rich kind of bunch of variables that I get to work with here. And when we look at the results, this is what we find. So unsurprisingly, of course, we find natural scenes such as coast, valley, mountains, and forest trees as being beautiful. But surprisingly, we do actually also see this built-up environments as well, aspects of the built-up environment. So for example, characterful buildings such as cottages. This is all English data, so that's why it's typically we get cottages in there, but also a lighthouse as well. And also bridge-like structures such as viaduct and aqueduct were coming out as being rated as more scenic from people. If we look at what's unscenic, unsurprisingly, of course, it's the kind of the industrial highways. People are kind of rating the images down for that reason. But interestingly, we also see this, there were features we can also extract from the neural network. So we get no horizon. So if you can't look out into the view, people actually rate it down. I thought that was really interesting. And something we saw with the neural network when I was making his predictions, that just because it's green doesn't mean it's really beautiful. In general, people are rating pictures down if the area of grass is flat and it's just uninteresting as well. So, so what can we say with the evidence we have so far? So yeah, we can say something about green space. So of course, flat and interesting places are not necessarily beautiful. Green spaces that contain trees and valleys and contours are more pleasing to the eye. It might be worth investing in these characterful buildings and beautiful bridges. It might not be a complete waste of money because they might be linked with us having a boost in our everyday happiness. But what I'm really actually trying to do now, and this is mainly work with Stephen Law because I'm mainly working commercially for the most part. So we're actually trying to look at architectural features as well because we'd like to give more meaningful advice to policy. So one of the things we're looking at is also one architectural feature we can pick up on is blank versus active frontage. And here, a blank frontage is when you walk down a street and it's got like walls and it doesn't look like you can actually interact with the space around you. Where there's an active frontage, there's windows, there's doors, it feels like a place where you can interact. And if we look at how it correlates with beautiful places, there is a strong correlation between active frontages versus building frontages. So it is still early days, but I'm really excited basically about what we can do with AI. And mainly because in the past, design decisions for buildings and city infrastructures have been limited to opinions of few people, right? So it's been, maybe the mayor, the city planning officers, architects, builders, but these design decisions actually impact millions of people. So I think it's really great how we can use AI to gain insights that were previously unfeasible from the preferences of tens of thousands of people to inform how we might design beautiful places that we actually want to live in. So that's it for me.
Thank you very much, Chanuki. That was really fascinating. We've got a lot of questions through Slido, but we only have about 1 or 2 minutes for questions. So you can either do them short and we can get through a lot, or it's up to you, but just as a heads up. So the first one that has 11 votes, so a lot of people want to know the answer, is from Leah. How are you defining beauty?
Oh, so I'm not defining beauty. I'm letting the model tell me what defines beauty. So this is where I'm extracting features from the neural network. And then I'm doing a statistical analysis and then trying to figure out what's actually beautiful. So I think that's interesting because we can crowdsource the idea of beauty and actually we can understand what a collective understanding of beauty is, because I think that's really important, especially when we're trying to go to policy decisions with that.
Brilliant. Another question with a lot of votes from Mark. Does the lighting of the images make a significant difference, i.e. sunset or sunrise light, as opposed to midday or sunny to overcast days?
So we did do a statistical analysis in general just to make sure image quality wasn't making an impact, and it didn't look like it did. But sometimes context does matter. I mean, luckily we're using images from Geograph. Like originally we're using images from Geograph, and they tend to be quite stable. But the better images is actually Google Street View, because they just do them all like in one go. And you can kind of hope that you don't get that much variety. But of course, I think sometimes I've noticed if it's snowy, somebody would have rated it up, and it's not about the context. It's because the snow just makes everything look beautiful. So there is a little bit of that in the data.
Fair enough. Fair enough. Another question from Trish. This is fantastic. Is your rated map available for the wider public?
Unfortunately not, but I mean, all the papers are available. So yes, you can kind of have a look at that. I did actually have a website where I had it working, and then it stopped working, and then I didn't have time to update it. I don't know. Maybe if there's a web developer out there that wants to help me, I'd be happy to release the data and they can create a map for people to explore.
There you go. Awesome opportunity for someone. Okay, I'm going to do one final question from Keith. How have you considered the historic environment, e.g. historic buildings, as part of including human constructs in measures of positive environments?
So I don't really I just take whatever buildings are there at the time period. I'm not looking at very specific styles of buildings. I have to say the data is probably biased more towards historical buildings because we're taking images from all around England. I would be very interested in doing this research in other countries, especially where there might be modern architecture, and seeing, what happens. There are probably certain biases with the research because England definitely has a lot more historical buildings and these really charming buildings as well. So that is something to kind of keep in mind with some of our findings.
Chanuki, thank you so much. I'm so sorry to cut you short. Anyone who's had more questions over here in Slido that we didn't get time to get to, I'm sure Chanuki would be happy to take questions, or you can get in contact with her on Twitter or email or whatever is best. Thank you to all the speakers we've had in this session for your set of talks. So much variety, but all so interesting.